Good morning or good afternoon, depending on what time you're watching this. I wanted to put a quick presentation together just to go over a few things to make sure we're all on the same page. I know you've had the opportunity to read this, but that doesn't mean you have read it, and even if you have read it, doesn't mean you necessarily understand it. Right now, we're going over some things about mixtures. Let's think about what we've done pretty much for the whole semester if we go back to the beginning of January. We started off talking about elements, and we spent a ton of time with the periodic table. Effectively, we were looking at the simplest pieces of matter. Eventually, we took elements and started putting them together. We discussed compounds for a while. We had ionic compounds, we had covalent compounds, but either way, we had more than one atom that was stuck together. For examples like water, ammonia, methane, carbon dioxide. All of these would be covalent compounds because they're all nonmetals, but we did spend a lot of time with ionic compounds as well. What we've moved into at this point are mixtures. Again, things that you have experienced your entire life. But by definition, when we look at what a mixture is, we just want to look at it as just at least two or more things that are put together that aren't chemically connected. So that's kind of the key component there, is that we put a couple of things together and they don't turn into basically a new substance. When we take carbon and oxygen, and under the right circumstances, it makes a new substance, carbon dioxide. So that's not a mixture. When we take vinegar and baking soda, and we see the gases coming out of it, that's not a mixture. That's a reaction. That would be a new compound being made. So with a mixture, we put a couple of things together at least, and they're going to retain the original properties that they already had. This slide shows several ways of us to envision that. Starting from the left over here, this would be a couple of types of elements that we put together. So if we mixed silver and gold, we wouldn't expect the silver and the gold to bond together to form some brand new substance. The gold would still be gold, the silver would still be silver. It would just be a mixture of those two things. So we would have more than one atom in here, but you can see that they have not joined together in any way. The slide beside of it would show, this would be if we took a compound, say O2, oxygen, and mixed it together with gold. Again, they're just kind of hanging out together. They're not chemically bonding. They're not turning into a new substance. And that's the case for all of these images that we have here. So there's a number of different ways that we can make mixtures, but the key concept here is that when we put the two things together, they don't bond, they don't form a new substance, and as such, they're usually going to retain whatever properties that they already had. For example, if it's salty, it's going to stay salty. If it's something sweet, it's going to stay sweet. When we describe mixtures, there's two different prefixes that we can stick on a couple words to indicate what kind of mixture it is. The prefix hetero means different, and the prefix homo means same. So when we have a bunch of mixtures, such as the examples at the bottom here, we can kind of classify them as one way or the other. The key thing to think about is, does it look the same throughout, or does it not look the same throughout? Is it homogeneous, the same throughout? Is it heterogeneous, not the same throughout? So this is non-uniform or not the same. Homogeneous generally is. So if we look at our examples over here on the left, we can see the things that would be pretty easy to pick out where things are separate from one another. Cereal and milk, the ice and a soda. If we went out and dug up some dirt, we could see a bunch of differences, rocks, soil, and so forth. And even blood, even though it might look the same to us just as we're staring at it, if we looked at it under a microscope, we would see that there's a number of different components in the blood, and it's not actually homogeneous. It's not the same throughout. There's a number of different particles, and it's not going to be in a uniform distribution. We can contrast that with a number of the things over here on the right-hand side. Soda, steel, air, rain. Those things, the particles would be evenly distributed. You'd have a hard time pulling out a little tiny piece of steel and it not looking or being composed the same as another piece of steel from the same sample. They should all pretty much be the same. One specific word that we use with homogeneous mixtures is a solution. So a solution is a homogeneous mixture. It's uniform throughout. we can't really, if you're looking at this picture, it just looks like blue stuff. We can't see the particles that are turning it blue. Whatever's been mixed in there is dissolved. They're dissolved uniformly, and we can't see one part for the other. It doesn't separate on standing. In other words, if we let it sit here for a while, we don't start getting particles coming down to the bottom. So you've been exposed to these throughout your entire life. A lot of drinks that you have, it's got sugar dissolved in it, a soda, tea, coffee. If you wear contact lenses, contact lens solution, which has usually a salt type of substance inside of it, it's going to be a uniform type of thing. When we put a solution together, there's going to be two different vocabulary words that we use to make the solution. There's a solute and a solvent. And by definition, usually the solute is the thing that gets dissolved. The solvent is the thing that kind of does the dissolving. It pulls the particles of the solute apart from one another. The solvent's not always, it usually is, but not always the one that's there in the greatest amount. There are some solutes that are just very good at dissolving, and we could keep adding and keep adding and keep adding. But generally the solvent is the one that's there in greater quantity. It's usually a liquid, although sometimes we can actually make a solution, or we can make a mixture. We can make a metal solution. To do so, we would need to melt them to begin with and then put them back together. Some examples of that would be like brass. And so there's metals that we can melt and mix together and then cool back off, and we can have a metal solution. The air around you can be considered a solution as well. So it's not liquid, but most solutions are liquid. Most solutions have water in them. And we've got some kind of solid that's going to be dissolved in the water. So we put the solute in the solvent, and the solvent dissolves it. And then what we're left with is a solution. Some other solvents that you might have around the house would be like rubbing alcohol. Most of the cleansers we have maybe possibly an alcohol or a vinegar-based solvent to help us to clean things better. Another couple words that deal with this are soluble and insoluble. Basically, this means can it dissolve, and it can't dissolve. Certain substances will not dissolve. A lot of things will, but one of the questions we had on one of last week's assignments was, does everything dissolve in water? Most of you all correctly figured out no, it doesn't, because if everything dissolved in water, then you couldn't put water in a glass, you couldn't put water in a cup because the cup would dissolve. The picture we have here is something like an Alka-Seltzer tablet. We put it in water, it dissolves easily. However, if we put oil in water, those two things do not mix to the point of making a solution. So this would still be a mixture. It would be a heterogeneous mixture because the oil does not dissolve inside of this. So that would be considered to be insoluble. Another couple words of saturated and unsaturated. A lot of y'all with your videos kind of started off okay with this, but then we got to the word supersaturated and it got a little bit confusing. The terms saturated and unsaturated just kind of depend upon how much solute is dissolved in there. There's a maximum amount based upon the amount of water we have. There's going to be a maximum amount of solute that we can put in there at a given temperature. So for example, if this was pure water and we put just a couple of grains of sugar in here, we would describe that as an unsaturated solution. And the reason it would be unsaturated is because it is able to dissolve some more. It's not full. I kind of think of this word saturated as being full. So this is not full of solution. The one on the right, there's evidence that it is saturated, and the evidence that it's saturated is that there is, if this is sugar, for example, there's sugar on the bottom of the glass. If this was an unsaturated solution, we should be able to stir this, and the rest of this would dissolve. A number of you said that this would be considered to be supersaturated. Now, supersaturated is not something that tends to happen in our everyday lives. I'm going to try to use the analogy here of the sponge for saturated, supersaturated, unsaturated. So this sponge is dry right now, so I could consider this to be unsaturated. And if I put just a little bit of liquid in here for some stupid reason, poured my coffee on here, it would start getting more saturated, but I would describe this as unsaturated all the way up to the point where it just would not absorb any more that we had on there. Now, in real life, I can't make this absorb any more than it ordinarily can. And that's what the term supersaturated means. Supersaturated means it's going to absorb more than really more than it's supposed to. Now, if I could magically make this sponge larger, that's really the only way I can make a sponge absorb more, is if I could temporarily make this bigger and then allow it to absorb as much as it could and to get it back to the saturation point. And then if I could somehow magically shrink it back down to this size and leave all the water in there that was in there when it was bigger, that would be supersaturated. So effectively, it's holding more than it normally can. And you're probably saying, well, that can't happen. And then that's true. And we couldn't do that, which is the same reason why with a supersaturated solution, we normally can't do that either. Whereas I was using the analogy with the sponge of making it bigger, one of the things that we can do with a liquid to make it be able to dissolve more is to heat it up. So if I take this substance on the right, if I put it on a stovetop and heated it up, it's very likely that at some point this amount would dissolve. So the amount that we're going to be able to dissolve is going to go up based on temperature. And then if we cool it back off, then the amount that should be able to stay in is going to go back down. However, there's some circumstances in which if we have the right kind of glass and we've got the right kind of substance and the conditions are just right, as the liquid cools back off, the solute stays dissolved. So in effect, more stays dissolved than ordinarily is even possible. And then if there's the least little bit of disturbance with that, then it will come back out of solution. I'll post a video from YouTube if you are interested in looking at that. It's actually pretty cool when it happens because it makes these really cool crystals that are on the inside. But again, it's not something you're going to see all the time. So I asked you last week with your project to talk about a supersaturated solution. Most of y'all were really confused about that because you just thought it just had too much in there. But that's not the case. Supersaturated means it's actually got more still dissolved than technically it's supposed to. And the only way we can do that is to heat it up to dissolve more and then cool it back down. Two other words were concentrated and dilute. And there's no real formula to say something is concentrated and dilute. These are really just adjectives that we can use to just describe a solution that we have. So this picture that we have here is pretty good. Concentrated generally just means there's a lot of solute and maybe not quite as much solvent. Whereas if it's dilute, we're going to kind of go in the opposite direction. We're going to have a lot more solvent like water and a lot less solute like sugar. So if it's concentrated, that would be like super sweet or super salty. Or if it was dilute, it would just be very, very weak is another way to think of it. Concentrated sometimes thought of as strong. You know, we've got a lot of coffee dissolved. We've got a lot of sugar dissolved into it. And so if we want to make something more concentrated, we're going to add more solute. If we want to make something more dilute, we're going to add more liquid to it. This is a term you may have in your house or you may have at some point in life where a lot of times in grocery stores we buy things that are concentrated, and then when we use them, we need to dilute them by adding water. There's some cleansers and some cleaners that are that way. It's just easier for the grocery store. It's easier for shipping for them to ship it very concentrated because they don't have to have so many bottles. And then we can take it home and then we add the water to dilute it. When we dissolve a solid in a liquid, there's really three ways that are going to help that happen. We can stir it, we can heat it, and we can make the particles as small as possible. And in all of these cases, what we're doing is we're bringing the water molecules in contact with the sugar molecules as fast as possible. If we stir this up, we're going to move them together. If we heat them, we're going to give them more natural energy so that they can come into contact. And if we grind it up, we're going to get these molecules from the middle of the sugar already out. Most of y'all probably know that. Gases dissolve in liquids too. So like with this Pepsi, there's carbon dioxide that's in there. Carbon dioxide doesn't like to stay in there. So a couple things that we can do to make sure the carbon dioxide stays where it needs to be is we don't want to shake it. We want to leave it be, which is the opposite of stirring. We want to keep it cold, which is the opposite of making it hot. And then the last thing is we want to keep the pressure really, really high. We want to do everything we can to be able to keep the carbon dioxide from getting to the surface of the liquid right here. So as long as we keep the dissolved carbon dioxide towards the bottom, it's going to stay dissolved. The only way that it's going to undissolve or come out of solution is if it comes up here to the very top. So as long as we keep the lid on, it's going to keep some pressure here, and no more airs, no more carbon dioxide will be able to come into it. If we keep it cold, the particles themselves, they're not going to move around very much, so they're not going to end up randomly up here. And obviously, if we don't shake it, it's going to make it less likely for those things to happen as well. So again, usually the things that make a solid dissolve, such as stirring, that's usually bad for a gas. It's going to, if you stir your Coke, if you stir your Pepsi, it's going to make it flat. It's going to lose its carbon dioxide. If we heat it up, the carbon dioxide is going to come out. And I think that was about everything that we have on there. Hope that was helpful.